Okay. Good morning, good evening, or good afternoon, everybody. Today I will talk about the microstructure and the mechanical properties of extruded rods prepared from recycled iron powders. Um, I am Xiaoli Zhao from Northeastern University in Shenyang, China. Okay, I will. Okay. Yes. Here is showing. Okay. Shenyang is shown here. Okay, uh, is located. It is located in the northeastern part of China. Okay, and now also now we are in summer. It's very hot. Uh, and this these are two figures. The figure one is a machine for preparing the roads using recycled iron powders. And figure 2 is the images of extruded rods prepared from recycled iron powder. And the upper, okay, this is the machine. Which one is to prepare the rods, okay? Extruded, the compact. And these two figures are the images of extruded rods prepared from the recycled iron powders. And this one is, okay, HRB 335, which is made from the type 2 powder received from the pellet. And this one is a Q235, prepared by the powder type 4 powder from received from the pellet. Okay. And then we after we get firstly we should use this machine to get the extruded rods. Okay, and this is rods we get. And then we need to if after we get the extruded rods, we prepare the specimens for microstructural observation, phase identification, and tensile tests. Okay, later we will talk about the tensile test, which is used to measure the mechanical properties. And we took two kinds of samples. One is cross section of the extruded rods. Okay, this red frame part is for the metallographic observation, SEMX and XRD testing. Okay, and the metallographic observation and SEM is to analysis the microstructure, and XRD is used to identify the phase constitution. And also, besides the cross section of the extruded rods, we also observe the microstructures along the longitudinal section of the extruded rods, which means this is the extrude direction. So the tensile, okay, this red specimen is for the tensile test, which is used to measure the mechanical properties, which means the tensile loading direction. Okay, loading direction is parallel to the extrusion direction. And also here is a green square. Okay, this specimen is for the metallographic observation and EBST testing, which the results will show in the later slide. And then we talk about the chemical composition of recycled powder and the designed alloys. Table 1 is chemical compositions of the recycled powders. There are two kinds of powders. One is the type 2 and another one is the type 4. And here the weight is 40 gram and 80 gram respectively. And here, okay, we can notice that the carbon contents in the type 2 or type 4 are different. The carbon content in the type 2 are more than that in the type 4. Okay. And using the recycled type 2 and type 4 powders, we designed two traditional alloys, HRB 335 and Q235. Okay, this table 2 is the ingredient of the designed alloys. Okay, and we use the parts of the powder is reduced iron powder. Okay, here type 2 4 gram to prepare the HRB 335 and the type 4 8 gram to prepare the Q235. Okay, and because we need to design the alloys, so we need to add extra elements. The weight is shown here. So the table 2 is the ingredient of the designed alloys. Okay, and because we want to extrude the rod, so the total gram is 700 gram. Okay, and the table 3 is the chemical compositions of the designed alloys, and we can find the chemical compositions of the HRB 335 are different with is different from the Q235. And then we measure the microstructures. Firstly is microstructures of the cross section. This figure shows the XRD results. From the XRD results, we found both the HRB 335 and Q235 are composed of ferrite. We can just observe the ferrite peaks in these two alloys. However, from the OM, this is a optical microscopy graph. We can find some second phase, this dark one. The second phase in the matrix, and the size of the second phase in the HRB 335 is much larger than in the those in Q235. However, it's noticed that they are not detected in the XRD pattern. According to the SEM results, the second phase in the HBr 335 is carbon and carbide, which is considered as a remaining carbon in the powder of type 2, and the second phase in the Q235 is silicide. The extrusion temperature, because the extrusion temperature is 1100 degrees C, which is lower than that of silicon melting point, which is 1410 degrees C. So even it's lower than the melting point. However, the temperature is very high, so the silicon can react with other elements to form the silicide. Then this is optical microstructures of the cross section. The etched solution is 4% little, and we soaked these samples in the 4% little for 40 seconds. The white parts we can find in both microstructures we can find the white and the dark parts. The white part is the ferrite, which is detected in the XRD pattern, and the dark part is the second phase. And because the second phase exhibits lower corrosion resistance, so it's easy to etching. And so the right figures are the magnification of the left images. Then we move to the optical microstructure along the longitudinal direction. We can find that in both HRB 335 and Q235, we can find some streamline along the extruded rods. This direction is the extrusion direction. We can find such streamline along the extrusion direction. And the second phase, the dark one, we have mentioned that the dark one are the second phase. So the second phase distributed along the streamline. We can see that a pre-existing second phase exists before hot extrusion and do not deform during the extrusion deformation because of their higher hardness than the matrix, because they didn't show the deformation, okay, along the extruder direction. These two figures show the clear images. Okay, then we move to the EBST results. This is the EBST images of the HRB 335. The arrow direction, okay, the arrow direction is the extruder direction, and the red line, okay, here the red line is the red line in the right figure is the low angle green boundary, and the black line is the high angle green boundary. From this figure, we can find that in HRB there are lots of low angle green boundaries, and here in this figure, the dark parts is the unidentified parts. We can find that the greens elongated along the extruded direction. Okay, so we can find this green elongated along the extruded direction. Okay, and also we can find some extrusion texture. This one shows that, okay, so we can find there some texture. The 101 texture fraction in the extrusion direction is here, okay, 42%. 42.1%. And then we compare the microstructure in the Q235. We can find, okay, here are the EBST results of Q235. We can find that more low angle. We can find that in this alloy, the low angle green boundaries are, the number of the low angle green boundaries are much smaller than those in the HRB 335, and we did not find the extended green along the extrusion direction, which indicates that dynamic recrystallization occurs during the extrusion, because, okay, we can find that greens here are equiaxed greens. They are not elongated along the extrusion direction. Okay, from here, also we can find the extrusion texture in the Q235 here, okay. And this is the 101. And the 101 texture fraction in the extrusion direction is 37.7%. Up to now, we analyze the microstructures. Then we move to the mechanical properties, and here shows three figures. Actually, there are many ways to evaluate the mechanical properties. Here we use the tensile tests to evaluate the mechanical properties. The above image, okay, the figure 1 is the tensile sample size, okay, and we, as we mentioned, these samples are taken from along the extrusion direction, which means, okay, during the tensile tests, the loading direction is parallel to the extrusion direction, okay, and the size is shown here. And the figure 2 is the machine for tensile tests. Okay, so we use this machine to pull this sample and to do the experiments. The experiment is carried at a room temperature, and the tensile speed is 0.5 millimeter per minute. And before the tensile tests, we should polish our specimens with emery paper. And after the tensile test, we can get such sample, the fracture occurs in the sample. Okay, actually, if we notice this is in the middle of the sample. Actually, from the tensile test, we can get yield strength, tensile strength, elongation, as a stress strain curve. Also, we can get the reduction ratio. Okay, actually, we can get a lot of parameters to describe the mechanical properties. Okay, the figure in the red square show how to get these parameters. Figure 1. Okay, here we can show, okay, this is actually this is the stress, and the horizontal axis is the strain, and the vertical axis is stress. Okay, finally we can get a stress strain curve, and from this stress strain curve we can get the yield strength, ultimate strength. Okay, and this is a magnification image to get yield strength. Okay, actually we need to draw a parallel line, like and move this parallel line to the 0.2%. Okay, then we can get the yield strength here. And figure 1 is the stress strain curve of the HRB 335 and Q235. We can find the yield strength. Okay, here we list the value here. We can find that yield strength of the HRB 335 is 405 megapascal, and tensile strength is 6024 megapascal, and the elongation. However, the elongation is small, and it's just 3.8%. However, the yield strength of the Q235 is okay. The yield strength of the Q235 is 236 megapascal, and the tensile strength is 393 megapascal, and the elongation. Okay, here if we notice the elongation is also the 27.4%, and the mechanical part. Okay, it's worthy to notice that the mechanical properties of the Q235 is comparable with the national standard. Okay, then we after we get some parameter to evaluate the mechanical properties, we can also observe the fracture surface. These are the fracture graphics taken from the fracture surface. We can find some dimples. Okay, there are many dimples and cleavage, caustic cleavage, and if we observe more in detail, we can find some. Found that at the bottom of the dimples, at the bottom of the dimples, there are many large particles. It is considered that the stress concentration. Okay, during the deformation, there are some stress concentration. The stress concentration occurs near these large particles, and the crack initiates inside the brittle second phase, and then cross the whole specimens. In Q235, the size of second phase is very small, so the numbers of dimples in Q235 are more than that in HRB 335. Here shows the mechanisms for crack formation. Okay, the uniform distributed second phase can lower the crack initiation possibilities. However, it will promote the initiation with increasing the particle size, and it is related to the related to the particle shape. Okay, here this figure shows the interface debonding around the two different particles. One is okay, the upper one is a round particle, the shape is round, okay, and the second one, okay, here is ellipsoidal particles. The shape is ellipsoidal, okay, and here we can find, okay, we call it debonding, okay, so there's the interface between the matrix and the particles. So the round face is equivalent to the micro void, and the ellipsoidal particle is equivalent to the micro crack for the crack initiation process. And then, okay, the potential, so the actually the potential quasi-cleavage crack initiation is micro void, cluster, and hard particles. And if the crack initiates, then it will propagate outwards, okay? And so the second phase plays an important role in the propagation process. Of course, it also play an important role in the crack initiation process. So we should take care of the second phase, and we should notice the size and the shape of second phase, size, shape, distribution, and the volume fraction of second phase. Okay, here is the summary of this report. Both the HRB335 and Q235 extruded rods are mainly composed of ferrite. Besides, they also contain second phases, which are formed before hot extrusion. The average sizes of the second phases in the HRB335 are relatively large. It is confirmed that the second phase in HBr335 is mainly carbon particles and carbides by SEM. It is considered to be the residue carbon in the type 2 powders. The second phase in the Q235 is mainly silicide. And from the EBST results, the grains of the HRB335 are elongated along the extrusion direction, and there are a large number of small angle grain boundaries in the grains. While the grains of the Q235 are relatively regular, there are 101 textures in both HRB335 and Q235, and the HRB335 has a higher texture content. From the engineering stress strain curve, it can be found that Q235 has better mechanical properties and meets the Chinese national standards. The poor ductility of the HRB335 indicates that large-size carbon particles and carbides are harmful to the elongation, while small-size silicide particles have less impact on the tensile ductility. Okay, thank you very much for your attention.
Luis, are you there?
Sí, gracias, Xiaoli Zhao. Gracias, Xiaoli Zhao. Yeah, before the questions, we need to acknowledge, I am going to acknowledge the grant from the CONCYTEC, FONDECYT World Bank for supporting this project. Okay, now we are going to start with the questions, okay? Xiaoli Zhao, I have one question before everybody. In the ingredients, in the second or third slide, I think is you have the ingredients, the amount of materials, the tables. Yeah, there.
It is here. Yeah.
Yes, in that table, you present HRB335.
Yeah.
And also a Q235. Okay, what is the amount of each of those ingredients?
Ingredients.
Yeah, those are HRB335. We understand that Q235, for example, is a type of material. It's a type of steel. So I understand that you added Q235 to the sample, to the powders. How much Q235 have you added?
No. Sorry, the Q235 is the designed alloy. Okay.
Is the result alloy, right?
Actually, we get we get two kinds of powders, the type 2 and type 4. Yes, and we use these two powders to prepare the HRB and Q235. So now we have two kinds of alloys.
Excellent. I understand. Nice. Okay. Nice. Thank you. Now, so we use type 240 and type 480. Those are the ingredients, and the rest, and all of the rest as well, to prepare Q235 and to prepare HRB3. Okay, understand. Now, what type 240 and type 480? There are information in the literature or in the information about those type of iron powders.
If you have 40 is the gram. Okay.
Yeah. Okay. Type 2 iron and type 4 iron, right? You buy type 2 iron and you buy type 4 iron, right?
Yes.
Yeah, okay. Those information, if you provide us the information, is in Chinese that information, or is it in English, the information of type 2? When you buy that, they give you information in English, or you give us information, or they give you information in Chinese? In type 2 and type 4. When you buy that.
And type 4 is powders received from Peru.
Yeah, okay. Nice. Okay. Yes, and now, so you add carbon, okay, pure iron. When you say pure iron powder, BAL, what this means BAL? BAL.
BAL means, okay, we actually totally, we need to prepare the 700 gram, okay? And we add 40 gram, the recycled, reduced iron powder, and we add the manganese, silicon, and others are the BAL, which means the balance.
That is the difference, right? The difference. Okay.
Balance means left. Okay.
Left.
For example, 700 minus 40 minus 9.8 minus 4.2. Okay, it's a balance.
Okay. Okay. Excellent. So that the difference between table 2 and table 3. Table 2 is the ingredients of the designed alloys, and table 3 says the chemical compositions. It means that once you have the powders, you use EDX to estimate the chemical composition, right?
Yes.
Okay, excellent. Okay, thank you. Now it's very clear that this is very clear for me. Now, you can go to the next slide when you etch the rods. When you etch. No, the next one when you use a solution to etch. That one. You said etching solution 4% nickel. What does mean nickel?
Nickel is a mixture of HNO3 and alcohol.
Okay, nice. Okay.
HNO3 is 4%. Okay.
Okay, nice. Thank you very much. Well, before passing to the other attenders for the other questions, could you can you send us your PowerPoint as well when we finish the talk? Can you send us the PowerPoint, please?
Yes, of course.
Okay, excellent. That's great. Okay, Now, start with the questions. I will speak a little in Spanish. Okay? Estos resultados son los resultados, muchachos, estos resultados son los resultados de las varillas. Ya Xiaoli Zhao ha presentado en esta charla los resultados de las varillas obtenidas, tanto las microestructurales como los resultados de mecánicos. Questions, preguntas, questions to Xiaoli Zhao. Raise your hand, levante la mano. Okay, first we are going to start with Ángel Bustamante. Ángel Bustamante's question.
My question is, please poke the lamina of the diffraction X-ray. From diffraction X-ray, poke the slide.
Yeah.
See, because I don't know what's the meaning to have to iron what class of the iron, un oxide or element iron pure because it's very intensity line is there in this position, no?
Yeah,
or is element oxide, hydroxide. I don't know what the structure to show in the iron, please.
This wires? You mean this wires?
Yes, Professor Bustamante is asking if there is a possibility that if there is an hydroxide or an oxide of iron oxide or iron hydroxide. Is there is any possibility?
Or only element, no sé.
Or only the iron.
You mean the XRD patterns, yes?
Yes.
Actually now, because powder was reduced, so actually now it is a metal. The matrix is a metal.
Ha encontrado metálico ese profesor, porque son los que ya se ha procesado luego de hacer toda la reducción y todo eso.
Sí, debe ser hierro alfa.
Sí. Okay.
So actually, yes, this is alpha ion. So it is a ferrite.
Thank you very much. Thank you very much.
Okay.
You're welcome.
Okay. Maricela Espinosa, your question.
Hi, thank you very much, Xiaoli. I have two questions.
Okay.
The first, why do you don't put sulfur and phosphorus? I know it's a little mass, but why do you didn't put in this component? Sulfur and phosphorus, yes. No, it's important.
You mean why I did not add sulfur in this alloys? Yes.
Yes. Phosphorus.
Actually, now we just try to design the HRB 335 and Q235. These are actually there's two traditional alloys, and the sulfur in the iron-based alloys is harmful to the mechanical properties. So we need to avoid the sulfur.
Oh yeah, okay. And the particular size, the other question, the particular size is different, maybe affect the reimpose of mechanical properties? Is the same?
Yes. Yes. The size and the shape and the type of also the distribution of second phase have a very important effect on the mechanical properties. Actually, because these two alloys prepared from the different powders received from Pelu. So after later, maybe we need to try to regulate the size of the second phase.
What is the average size in
average size?
Mhm.
Actually, you can see it's very okay. Actually, we didn't measure the in detail, but I think it's okay. Maybe here, from here, 10 micro, like okay. If
10
we
micro.
notice this one, okay.
Yeah.
Later we should measure this in detail, and we should how to say count okay and measure the average value. Thank you for your comments.
Thank you.
Okay, thank you very much, Maricel. Shugo, question, Shugo.
Hi for everyone. I want to thank Professor Xiaoli Zhao for the nice talk. And I have two questions actually. In the slide number 4,
Okay.
this a table. Okay, there is no iron in the in table number 3.
3 is a balance here, like this one. Okay. Okay, the balance means okay, the remaining the matrix. Okay, so we usually if we check the mechanical compositions, we didn't measure the matrix like the main element error. So usually if we write the iron here, we will write the balance.
Okay,
like this one.
Okay, understood. And another question is, in what sense the presence of carbides and carbon particles affects the mechanical properties of the system?
Pardon? So you mean the this
in the summary particle. Yes, in the summary you write the presence, the second phase is mainly particles, and the three
third one
the productivity indicates that sealers are harmless.
Yes, if the particle size is very large, it's harmful for the ductility, which means the elongation.
Okay.
Actually, we need to get a uniform distributed small particles to improve the mechanical properties.
Okay, Professor. Thank you.
Okay.
Thank you very much, Xiaoli Zhao. Thank you very much, Shugo. Thank you very much. Any question? Any other question? ¿Alguien más tiene una pregunta? More questions? Okay.